Okay. Can you see my screen?
Yep. Yeah.
Okay, perfect. Good morning, everybody. I'm Giuseppe. You already know me, so I think I'm going to skip the presentation. So today, I want to talk about recurrent models first, and then I want to introduce the concept of the attention mechanism. But let me start with two disclaimers. First of all, we'll be focusing on intuition only. So many further technicalities that actually make this stuff work will be left aside for this talk. And also, let me give you a temporal picture of these techniques and specifically within the NLP community. The recurrent models, which are a type of neural network, actually have been gaining hype between 2012 2014. But what happened is that in 2016, the publication of the paper "Attention is All You Need" changed everything. But I'll be there in a while. So let me start from a general overview of neural networks. You know, at least in a supervised setting, you have some kind of input, X, that goes into the network, which is characterized by some parameters theta, and then the network produces an output label. Then the magic begins, because from the output label, we can compute the loss. So you can think of the loss as a way to say, how far did we go from the actual labels? So the ground truth labels. And from the loss, we can compute the gradients, which are, again, a way to say how high was the influence of each parameter in the network for the final loss. And then with the gradients, we can use one of the most brilliant algorithm in the computer science field, which is the backpropagation algorithm, which is used based on the gradients to change the weights of the network in order to reduce the loss. So this is a very general overview. Let's see how this fits for recurrent neural networks. So recurrent neural networks are a general architecture for modeling sequences. So general neural network architecture. We have, again, an input X that goes into the network, which is characterized by a hidden state, H, which is, you can think of it, H as a floating point vector. And then from H, we are going to produce a final output label. So this is very similar to what I've shown you in the previous slide, except for the fact that the recurrent neural networks are meant to encode and model sequences. So you apply the recurrent neural network for each step of a sequence. So your input is a sequence. You can think of a sentence, you can think of stock prices, you can think of many sequences. So the real big difference in recurrent neural networks with respect to, like, let's say, convolution neural network and feed-forward neural network is the presence of a recurrent operator. So the hidden state of the network at each time step doesn't depend only from the input, but also from the previous version of the hidden state itself. So by the end of the day, we are going to have three matrices, which are a way to say that the network is in principle very shallow. We are not going to have so many weights and parameters as you can imagine, for example, in convolution neural network. The recurrent neural network is very shallow. The recurrent neural networks, as I said, is applied each time step. So one time step at a time. So I just changed the input. Now we have a sequence in the bottom part of the slide, and we are going to apply the recurrent neural network for one step at a time. So if we think of the RNN as enrolled along across the time, we are gonna easily see that the RNN, even if it's shallow in its architecture, so we have only three matrices to describe the network, it gets deeper and deeper and deeper if we compute the recurrent neural network across time, so many time steps. So this is a computational graph, or RNN, and you can see that, of course, you can compute the backpropagation, as I mentioned in the second slide, for every time step. So in this case, since the network is shallow, but it's deeper in time, it's deep in time, what practitioners are used to call this operation is the back propagation through time, because when you change the weights of the network, you're actually changing the same matrices multiple time, but you are going to do this through time. This is a very general overview of recurrent neural networks, and it's pretty much it. So if you're interested, just I posted in the slide, I linked in the slide a very nice blog post from Andrea Pasini, and you can find many details, much more details over there. So this is the basic RNN architecture. Then we can play with the architecture. For example, we can stack different layers in recurrent neural networks. So in this setup over here, you just take the output of the first layer and fed them to the second layer, and then you use as output the output of the second layer. So this is an example. You can also do something different. You can, for example, use two different hidden states, and the second hidden state is something that computes the input sequence from right to left. So you have the dependencies that goes in the other direction. You can then just concatenate the two vectors, and again you will have a matrix in the top part of the recurrent neural network to compute the final output label. But those are two possibilities. In general, we can play with the RNN architecture to make it more capable of generalizing. And in general, we are trying to improve the capacity of the model. So you can think of encoding sequences in this way, in a much more general way. So let's see a few pros and cons of this architecture. So first of all, weights are shared across time. So the number of parameters is low. If you think about that deep convolutional neural network like ResNet or VGG, there are many more parameters than a vanilla RNN. And also that inputs get equal treatment no matter of their placement in time. Also, if you think of the architecture that I just showed you, you can easily see that you can continue the computation as much as you want, as long as you want, because this network, as is defined, can handle sequences of arbitrary length. So theoretically, each input is gonna have an influence on every future output down in the chain. And also, as I showed you, the architecture is very flexible. You can have stack layers, and it's very easy. Actually, in PyTorch, you can just say number of layers equal to something, and then it gets the network for you. That's for the pros. The big cons, the most important cons for recurrent neural networks is that recurrence inhibits parallelization. So if you are used to the fact that you can take the kernels and make matrix multiplication in parallel in many GPUs, for example, in convolutional neural networks, you can't do it in RNNs because each time step is dependent on the previous ones. So the computation is going to be much heavier from a computational point of view. And also that even if it's there, so the influence of each input to the final to the future outputs, the information flow gets cut by the problem of vanishing gradients. So there are vanishing gradients. So as I said in the second slide, actually, the gradients is a way to tell how much, so how was the influence, how greater was the influence of every input over every parameter in the network for the final loss. And so in the backpropagation algorithm, based on those influences, we are gonna change the weight. So the greater is the influence, the greater will be the change of the parameter. So the greater will be the impact of that input point for the final loss. So if the gradient vanishes, so the smaller the gradient gets, and Actually, the farther in the past we go from the current loss, the smaller the gradient will become, and the smaller will be the impact on the update of the network. So this is a very well-known studied problem, and we're gonna try to fix it with the use of the adoption of gated recurrent neural networks. So let's see a few applications of RNNs, and then we're gonna move to the gated recurrent neural networks. Language modeling. Modeling language entails predicting the next item. It can be either a word or a character given a context. So imagine the sentence, back at the grocery store, Clara bought a blank something. So the fact that there's grocery store in the sentence tells us the grocery store related stuff should be more likely for that spot. So and the fact that we are using the word likely in our mind is it's something that suggests us that we are thinking of modeling a probability. So let's see how this sentence can fit in a RNN. So we are applying one word at a time, and when I say word, you can think of that word embeddings that Flavio presented you in the previous talk. So you take the word and you apply the RNN unit to each of them. And then at training time, you want to have as the ground truth label for language modeling task, the next word in the sentence. So if you have the in the first step, you have the, and the ground truth label will be grocery. And in the second step, we'll have grocery and the output label will be store, because the ground truth label is the number that we, or actually the label that we are gonna use for computing the loss and updating the weights. So next word as output ground truth label at training time, and then at inference time, when we have produced, let's say the grocery store, the grocery store Clara bought A. When we are asking for a word as output of the recurrent neural network, the RNN is just gonna produce a probability density function for across all the words that are in our vocabulary. So we hope that the hidden state here, HN, of the recurrent neural network is gonna encode the context of the sentence. So it's gonna produce in that very step a probability density function that lets words as cake or cola prevail on others. And so this is the task of general overview of the task of language modeling. Of course, you can do this also with characters and so on. Much more generally, we can use the network as an encoder for further downstream tasks. So here I presented the task of sentiment analysis. You can take the sentence, for example, this is a movie review. Oh man, this movie was awesome. And you can use every word to, you can pass every word into the recurrent neural network and use the sentence representation. So you're gonna use the last label, the last hidden state of the recurrent neural network as the representation of the sentence. So over here we have HN, which is a floating point vector. So it's going to be probably a NumPy array, 512 floating point vectors. So you can use those vectors to train a supervised classifier. For example, here I suggested a subvector machine. So you hope that finding it's a hyperplane dividing, for example, the good or bad movie reviews is going to be simpler because the hidden state has encoded the semantics of the sentence. Actually, you can also use the previous time steps. You can just keep track of them and then concatenate all of them and not use only the final hidden state. So let's move on to the neural machine translation. That it's probably one of the most story of success in NLP community, in the usage of our recurrent neural network in the NLP community. here we have a first neural network, a first RNN, which gets the sentence, the source sentence that we want to translate. For example, the sentence, the cat is on the table. Then from this sentence as an encoder, we can use the last hidden state that is produced by the network, in this case HN, and use it as the first hidden state of a second recurrent neural network, which is in charge of producing the translation. So at each time step, we start from the hidden state that was produced by the encoder network. We produce an output label, and if the network is trained, we are likely going to produce the token IL. And then we fed the token IL back into the network, into the decoder network, and we are going to produce the word gatto, and so on in the translation. We have had the trick here is that we can add to the vocabulary the token end of sentence. So we let the network decide when the translation is concluded, so is finished, because we are going to take all the words that were produced by the decoder network before the end of sentence token. So this lets the translation be, the source sentence, the sentence that we want to translate, and the target sentence be of different length. And this is a very important result in field of natural language processing. So let's see a few more examples, probably the funniest one. RNNs for image captioning. Now that you have understood the rationale of the recurrent unit applied every time step to a sequence, we can play with the input. For example, we can just choose another different input. So you don't have the input to be a sequence. For example, you can try something different. And in this example, you can take a picture and you can feed the network with the picture. You can either use the pixels or for example, some sort of encoding of the picture, and then you use these to enforce some relationship in the network. The output label in this case could be, for example, a textual representation of the picture. So you can train the network in this way. So for example, in this example, we have a human hand holding a hedgehog. And so once you train the network in this way, you are gonna have a recurrent neural network architecture, which if you use an image as an input, you are going to have a textual representation of that image. So you are going to produce a caption for that image. And if you understood this inner functioning of the recurrent neural network, so the intuition behind image captioning, you can also understand that we can generate actual stories about images. And okay, this is by far the funniest slide in the presentation. So if you are sleeping, just wake up right now, because it's very funny. If you take a recurrent neural network that was trained on some text, for example, a romantic novel, and then you fine-tune this network to do the actual image captioning task, you're going to have a description which has the style of the original training. So for example, romantic novel. In this case, the story about this image is fantastic, because he was a shirtless man in the back of his vine, and I let out a curse as he leaned over to kiss me on the shoulder, which is pretty accurate for what's inside the image. And also, he wanted to strangle me, considering the beautiful boy I had become wearing his boxers, which is again incredibly, let's say, matching for what's depicted in the image. So you can find more examples in the link down below. Okay, so we talked about vanishing gradients. So let's introduce the concept of gated recurrent neural networks and how to overcome the problem of vanishing gradient. So let's imagine the sentence. Yesterday, I visited my grandma and I bought there a bunch of stuff. Also, I installed that Alexa device as you asked. I have strong doubts that it will work, but when you're ready, we can try to video call something. So we as humans are gonna be easily filling this box with hair, because we can try to video call hair. It's easy for us, but it's very difficult for recurrent neural networks, because it is very, very long term dependency from these two words in sentence. So the main idea, and again, this is a problem of vanishing gradients, because the gradient on the word grandma would be very, very, very small to update the network. So to solve this problem, the main idea behind there are actually two main ideas behind gated recurrent neural networks, which are, first of all, we can add explicit memory in neural network architecture. So we have a memory cell in the architecture which is used to keep track of let's say a memory, some sort of memory. And also, and it is very brilliant, we are gonna let the network learn how to use it. So when read from the memory and when write to it. And I just want to point out that this idea was published in 1997, and it's incredible how it just stays there for 10, 12 years, and then it just emerges as one of the most important sequence modeling architecture. And it's, by the way, from the team of Jörg Smith-Huber. So this is an example. I just don't want to give you too much details here. This is an example of one of the most important gated recurrent neural networks, which is the long short-term memory. And I took this slide, this representation, from this very neat blog post, and just check it out, because it's very well done. What we can see in this architecture, at least the intuition behind this architecture, this new recurrent architecture, is that in this case, we have, first of all, an explicit memory cell, which is something on the top part of the chart. And we also are gonna have three different gates. So the gates are mechanisms to let the network understand and how to use the memory. So we have a forget gate, which is a way to say how much memory I forget. We're gonna have an input gate, which is how much input I had to the memory, and an output gate, which is how much memory I do output as the hidden state. So be sure to check the blog post for much more details, but it's in principle, if you get the underlying intuition behind recurrent neural networks, gated recurrent neural networks are just a practical way to solve the problem of vanishing gradient. So that's all for, I'm sorry, I'm not watching at the chat, looking at the chat. I don't know if there are questions. I don't think so. Okay, so let's move on to the last part, which is the attention. The attention is, I didn't choose the picture randomly, if you are asking. The problem of attention is motivated, the usage of attention is motivated by our ability to focus on salient information and discard the rest. So if you are a cocktail party, and you typically want to focus on the people who you are talking to, and you just want to get rid of all the noisy background around you to understand what the people is saying to you. So based on that, between 2014 and 2016, we came up with a groundbreaking innovation for sequence modeling. And this application is, this technique is as innovative as to the extent that you can say that temporal constraints get loose, and if not discarded at all. And the main idea behind the attention is that we are gonna let the network learn how to discard information. So we don't want to add any type of information, but we just want to let the network understand which is the most important part for the prediction in the case. So let me give you two examples very quick. The first one was an application that I just showed you, the neural machine translation, which is probably the most important application of attention right now. So we have those the two recurrent neural networks, the encoder and the decoder, and Badanu and et al. in the neural machine translation by jointly learning to align and translate paper argue that the final hidden state, if we use only the final hidden state to encode the entire input sequence, we're going to have some sort of bottleneck of information because it's only a single vector representation. So they came up with this idea that for each step in the decoder, we are going to do the following. So let's say we are in the first decoding step. So we are going to produce the first token in the Italian sentence. So we multiply the hidden state of the decoder with every hidden state in the neural network encoder. Then we normalize those values. The multiplication actually, it can be, you can use many strategies over here. You can do, for example, the dot product or just the cosine similarity. It's up to the application. There is a general framework. It's not, you are not going to find a attention class in PyTorch. It's a very general framework. So as I was saying, you can now normalize those multiplications, and then you're going to have some sort of probability distribution. So you're going to use this probability distribution as attention weights, as a way to say, to quantify the importance of every time step in the translation of that single time step in the decoder. So this is very powerful because now you can see that we have a direct connection from the word "the" to the word that we are trying, to the hidden state at least, that we are trying to predict in the decoder. So once you have the attention weight, you can just concatenate them. You can create a vector. You can concatenate them in the hidden state of the decoder. And then from this representation here, you can just output again. You can use the log softmax, the softmax that Flavio showed you, and you can compute the final output token for the translation, which is in this case IL. And so the very important thing here is that you let the network understand these weights over here. This is going to be a matrix also. You let the network understand this is part of the gradient descent backpropagation algorithm. So you don't choose those weights. It's the network that learns those weights by itself, and it's a very powerful. We gained Badanu gained a very boost in performance by using the attention. And the final application is the generating sequences with RNNs, which is a paper from Graves, which now works for DeepMind. So through attention, in its experiments, through attention, the synthesis network focuses on a few letters. So the task here is to produce and writing from a textual representation of some text. So and Graves used the attention mechanism, and you can see that it's working pretty well because on the left part you can see that only the top line is real, and all the other lines, all the other samples are generated by the synthesis network, so the decoder, and the decoder makes use of attention. So you can see on the right the attention weights in a let's say a heat map, the amount of attention that the decoder was looking for the each letter in the input sequence. So when producing a single, here the network produces the X and Y coordinate of a pen in the sheet. So you get the point. So we have the attention while generating the pen and writing with respect to the letters in the input sentence, and this is very powerful. So last few slides, the attention from 2016 up to nowadays. In 2016, as I mentioned in the first slide, the paper attention is all you need is published, And the paper introduced the transformer architecture, which which doesn't use recurrent units anymore. And this is very powerful because we just lose everything in the sequentiality computation. So we don't use recurrency anymore. The architecture is an encoder-decoder architecture, as I showed you for neural machine translation, and it uses a clever associative attention. But just I don't want to go into details over here. The point is that the transformer became the building block of many renowned language models. Maybe you've heard of some of them: Vertex, RNN, GPT in all its variants, NT5, and many more. But as I said, there's no room for that in the talk. So I want to conclude. I just don't want to wrap up. I just want to give you some open points. First of all, the attention, as is defined, can be used as an explanation. Actually, if the attention can be used as an explanation, it's a topic of a huge debate in the community, in the NLP community specifically, and we can talk about it. And also the transformer architecture, which is based on the attention, again, is the enabler for new neural architectures. And up to now, we have at least 3 papers that use attention in the field of computer vision. And they beat the counterparts that are, for example, convolutional neural network, just by using only transformers, which is in turn a way to say that we are using attention only. You can check it out later. Those 3 papers are very well done. So I think that's it. Sorry if I'm late. Thank you for the attention. If you want to further